Log on, tune in, find out. Another good idea from Cambridge.
And he will speak about a completely integrable toy model of the nonlinear Schrodinger equation without dispersion. It's not linear. Did I? Okay, so it will be really non-linear.
Okay, thank you very much for this kind invitation. It's a pleasure to be here in Cambridge and to enjoy the lovely British weather, perfectly convenient for working.
Hey, it was good until today.
Yeah.
Don't complain that much.
So,
That's what they say to everybody who's just arriving.
it's your fault.
They organize
Okay,
the good weather for
so
your
first of all, I have to apologize. Yeah.
the microphone.
Oh, the microphone. Do you really need it? Oh, yes, because of
they are
this.
filming.
That's fine, because my first remark was not recorded. It's excellent. Do you hear me now? That's fine? Okay. So thank you very much. So my talk today is devoted to some mysterious evolution equation, which is not, in fact, a nonlinear Schrodinger equation, which is a toy model for something which sometimes arrives when you are looking at nonlinear Schrodinger equations in very degenerate geometries. And so I will spend some time. First of all, let me remind you that this work, the whole work I'm going to talk about, is a joint work with Sandrine Grelier, who is a harmonic analyst from Orléans. And so my starting point is the standard cubic nonlinear Schrodinger equation on any kind of dimension or even any kind of geometry. So M denotes some manifold, or Riemannian manifold, for instance, or anything. And the starting point is that for solving such an equation, so for solving the Cauchy problem for such an equation, usually you appeal to the standard iterative scheme, Picard scheme, for the Duhamel equation, which is written here. And it turns out that if you try to get estimates on this nonlinear Duhamel term, which is here, and you want this term to be estimated in the Sobolev space HS, it's essentially equivalent to have inequalities on the free Schrodinger group e to the it Laplacian. These inequalities are part of many other inequalities which are usually denoted as Strickhart's inequalities. So which tell you that the L4 norm in time and space, even for a finite time interval, is bounded by some Sobolev norm of f in HS over 2. This is almost a necessary and sufficient condition to prove local existence for the Cauchy problem with data in U0. And this is in fact a byproduct of a work we did with my colleagues Nicolas Burk and Nikolai Tsvetkov in 2005. So these, of course, if S is large enough, this is always true by Sobolev inequality, but this is not what we want. We want to have much better estimates for S very small, for instance, S equals 0, say, which means that you would be able to estimate estimate the L4 norm of the free Schrodinger group by the L2 norm of F in L2, the L2 norm of F, sorry. This is typically what happens in R2 if M is just a Euclidean plane. And more generally, we want to know what happens for more degenerate geometry, more general geometry. Imagine that M is, say, a torus or a sphere or anything. And the problem is that this S may depend strongly on the geometry. And if the geometry is non-trivial, this S may be very large, and it may be larger than the energy threshold. Why is that a problem? Because the energy threshold corresponds, S equals 1, corresponds to essentially the best conservation law we may expect for this equation, the conservation law of energy. And if we want to have global existence in the energy space, we need to be able to solve locally this equation with s smaller than 1. So if s is larger than 1, there is no way, we don't know how to solve such an equation globally. While it seems, I mean, with a positive energy, it seems to be reasonable to expect the global existence. So that was the starting point of our work. But once again, we are not going to look at this nonlinear Schrodinger equation, but rather a variant of it. So the variant I'm interested in is the Schrodinger equation when you replace the Laplacian in R2 by this operator, which is a degenerate operator. So if you want to talk about geometry, I'm in fact escaping from the Riemannian geometry, and I'm going to what people call sometimes sub-Riemannian geometry, in some sense. So this is a non-elliptic operator. This is sometimes called the Grushin operator. So it degenerates on x equals 0. But formally, it's of course like a Schrodinger equation, nonlinear, with a Hamiltonian, with this energy I was talking about before, which controls first derivatives in terms of g, which means that dx and x dy in L2. And the same rule applies. So to solve this equation in Sobolev spaces associated to g, in the sense that they are the domain of minus g to the s over 2, you need estimates of that kind. And we would like to have estimates with s smaller than 1 to be able to globalize. And it turns out that this is not possible. It turns out that this inequality is, in fact, only the trivial inequality is true, which corresponds to s equals 3/2. 3/2 is the dimension divided by 2, the dimension, not the algebraic dimension, but the so-called homogeneous dimension, where in fact the variables do not have the same homogeneity. So one of these variables has homogeneity 1, and the other one homogeneity 2. So that 1 plus 2 equals 3, and you are like in 3 space dimensions. So in fact, what I claim is that this inequality, and finally the iterative scheme for such an equation only converge for s larger than 3/2, which is in that case completely trivial, because you just estimate the standard, just use the standard Sobolev inequality. L infinity includes h 3 over 2 plus epsilon. So what does that mean? It means that this equation is completely supercritical. While of course if you look at scaling rules, you will see that scaling rules would give you something which means that the equation is subcritical, so you would be able to solve it. And in fact, this is absolutely not the case. So let me explain why, and why it's related to transport equations. In fact, if you start with this very simple function, it turns out that this function is a solution to this equation, which is also some kind of Schrodinger, but not exactly. I dy, so let me remind you that g is dx squared plus x squared dy squared, okay? So it's a strange equation. You can see that this f is solution of this. You can rescale because you have some homogeneity on g, as I already told you. And if you rescale, you see that the HS norm of Fn is like n to the s, while the L4 norm is like n to the 3/4. And finally, you observe that the free Schrodinger group, acts exactly as a transport equation, a transport group, okay? And a transport group means that you look at Fn, so you have a solution like Fn of x and y minus t. If you compute the L4 norm of this guy, you get just the L4 norm of Fn, which is like n to the 3/4. So if you compare these two quantities, you obtain that the inequalities, which is here, only holds for s larger than 3/2. So what is behind this? I mean, sorry for this mysterious introduction, but what's behind is, it turns out that this equation, with this nonlinear Schrodinger-like equation, is rather like a system of transport equations. Why? Well, to solve this equation, I mean, to see a little bit more about the equation, you introduce Hermite functions, which are related to harmonic oscillator. Why? Well, just because if you look at this operator, if you use Fourier transform in the y variable and make some scaling, you will be, of course, reduced to study the harmonic oscillator, okay? So if you introduce the eigenfunction of the harmonic oscillator, the well-known ones, and you model some subspace of L2 with these eigenfunctions, you get that on this subspace, which are infinite dimensional subspace, G acts as a transport operator. And of course, you can break the whole L2 space into these pieces. And finally, of course, if you introduce the orthogonal projectors onto these pieces, you get that our nonlinear Schrodinger-Grushin equation is in fact equivalent to this system. So in the left-hand side, you get just a transport equation with velocity 2m plus 1. And in the right-hand side, you get this funny nonlinearity, u square u, and then on u square u, you let act this projector, pi, okay? And of course, this um is just the component along this projector pi. So solving our equation is equivalent to solve this infinite system of transport equations, and you can understand why dispersion completely cancelled, just because, in fact, you only have transport equations, just transport equations. And so, in order to understand, it's a difficult problem. We are not going to solve it, unfortunately, today. But in order to understand this problem, you need to understand the structure of that kind of nonlinearity, which is a new kind of nonlinearity. You look at the standard cubic nonlinearity, and you compose with some Calderon-Zygmund projector. Here it's a little bit complicated, but when we saw that, we decided to look at toy models, and a toy model of such a system where, in fact, to start with something really simple, forget about the system, look at just one equation, but with such a projector here. And what kind of Calderon-Zygmund projector do you know? The simplest one is certainly what is called the Zeger projector. So let me change the landscape completely. So if you didn't like what I told you before, it's a good news for you, because I'm going to change completely the situation now. Rather than working on R2, I'm working on the circle. So just one variable. I'm on the circle, and I consider the so-called Hardy space. So the Hardy space is a subspace of L2 functions on the circle. I denoted by L2 plus, not by H2. Usually in harmonic analysis, it's denoted by H2, like Hardy. But here there are too many H's in this theory, so I decided to replace this by this H2 by L2 plus, which is, of course, a lack of respect to George Hardy. I'm so sorry about that. But now, if you look at this Hardy space, which corresponds to Fourier series with L2 coefficients, but only non-negative Fourier modes, okay? If you prefer, so here I put Z rather than e to the I theta, because, of course, there are two ways of understanding this Fourier series. The first one is, of course, a Fourier series on a version on the circle, and the second one is, of course, to think of a holomorphic function inside the unit disk, okay? And Z will be, in fact, the variable inside the unit disk, okay? So if you prefer, you have holomorphic functions inside the unit disk with traces which are L2 on the circle. And you look at the following funny evolution equation, so the same kind of equation before. Let me just remind you. here. Of course, if there is just one equation, you can forget about the velocity just by using the characteristic method. And so you are led to that kind of equation. Okay? And I claim that I'm going to solve this equation, to study this equation in a phase space which is not L2, which is a little better, which is a little smaller than L2, which will be the Sobolev space H1/2 with, of course, non-negative Fourier mode, which I denote by H1/2 plus. Okay? So H1/2 plus is the Sobolev space H1/2 with non-negative Fourier mode. So this is a strange equation that we decide to call the cubic Zeiger equation. Cubic Zeiger equation. Well, for trivial reasons, I guess. And I'm going to tell you about this equation and of many properties it has. So first of all, it's a nice Hamiltonian equation, you know. So if you introduce some symplectic form on L2 plus, which is just the imaginary part of the scalar product, the L2 scalar product with some constant here, which is convenient for normalization, but it's in fact not really important. And if you look at the Hamiltonian, which is just the L4 norm, okay, the L4 norm to the four, and you get that the Hamiltonian, and you look at the symplectic structure, which gives you some Hamiltonian vector field. You have an Hamiltonian evolution, and the Hamiltonian evolution is exactly this one. Okay. Why? Because if you take the differential of U4, of course, and you take the differential of U, you get 4 real part of U square U H bar. So if you take here this, and then you get that this is exactly omega of H in minus I pi of U square U. So I need pi. Why? Because I need a vector field which is in the phase space in L2 plus. So I need to project this guy onto L2 plus. And that's why I get this strange evolution equation, which is here. Let me write it for you, maybe for the rest of the talk. Okay. Now, other observations is that exactly as the nonlinear Schrodinger equation, of course, this is a conservation law, the energy, but you have two other conservation laws, which are the charge, or the mass, the L2 norm, the square, and the momentum. The momentum, which is, as usual, defined as minus I du scalar u, and if you prefer to see it in the variable z inside the holomorphic disk, the unit disk, it's just z dz u scalar u. And well, you know, for people who know how to deal with all these conservation laws in nonlinear Schrodinger equation, it turns out that this momentum always plays some very strange role in the analysis of nonlinear Schrodinger equations, because in general, well, it's not a positive conservation law, so it's not easy to use. Here there is a miracle, and the miracle is that this conservation law, this momentum, is non-negative. Why? Well, just because you have only non-negative Fourier mode. So if you compute this object by means of Fourier coefficients, you get this. And this is essentially the H1/2 norm. So that's why I would like to solve it in H1/2, of course, because I do have a control of the H1/2 norm by means of conservation laws. So far, it's rather natural to state the following theorem, which we proved when we started to study this equation. Namely, if you are given data in H1/2 plus, once again, it's just H1/2, but also in the Hardy space, non-negative Fourier modes, and there exist unique weak solutions, continuous valued in H1/2 plus, of this Cauchy problem. And moreover, if the data are a little more regular, say, hs for s larger than 1/2, then so is the solution. So how do you prove this? Imagine you have to prove such an theorem. So what can you do? In fact, the right way is to start proving the last part. Okay, so just try to solve the equation for large S. That's easy. That's easy if S is if you want to solve the equation for small time, because S larger than 1/2, you are in one space dimension, so you are in L infinity, and this is in fact a nice vector field on HS. So that's just Cauchy-Lipschitz theorem. But the problem is to have global existence. Global existence, of course, you need conservation laws. And the only conserved quantity essentially is the H1/2 norm. So what about the HS norm? Well, you could try to get estimate on the HS norm. Unfortunately, H1/2 is not contained into L infinity, so you need to do something better. And the idea is in fact an old idea which at least comes back to Brézis-Galouette in the beginning of the 80s, which is an estimate of the L infinity norm by the H1/2 norm times some logarithm of the HS norm, okay, to the 1/2. So that's a strange estimate. You know, you pay a little bit the fact that L infinity is not contained in H1/2 is not contained into L infinity by the presence of this HS norm, but only through some square root of a logarithm. So you plug this guy into the equation here, you apply Grunwald inequality, and finally you get that the HS norm cannot blow up, and you can even have a double exponential estimate, exactly as when you try to prove global existence to the Euler equation. Okay, it's exactly the same kind of Ludovic, Schrick, etc. And in fact, then for S equals 1/2, you just make approximation using the conservation of the H1/2 norm, using the Relish theorem. You get existence of weak solutions, and the hard part is, of course, to prove uniqueness, and that's exactly as for Ludovic argument. You can prove, once again, with some kind of logarithmic inequality and some kind of Schrodinger inequality, in fact, in that case, uniqueness of these weak solutions. Okay, so that's the starting point, but of course that's not the main purpose of my talk. I would like to tell you more about this solution. Now we have such a solution. We would like to know more about it, and it turns out that this equation has a very rich structure, and this is what I would like to tell you about today. So for this, I need to introduce linear operators on my Hardy space. And the first kind of an operator is what is called the Hankel operator. So you are given a function u in H1/2 plus, say. So once again, it's Sobolev space, and I define the Hankel operators, so still in H sub u from L2 plus to L2 plus. So it's an operator on the Hardy space, which is defined by this strange expression, P of u h bar. So it's not C-linear, it's just an anti-linear operator on L2 plus, but it's R-linear, for instance. And it enjoys many properties. The first one is that it's like, it's not exactly self-adjoint because, once again, it's anti-linear, but you have the same kind of symmetry properties. HU of H1 scalar H2 equals HU of H2 scalar H1. And moreover, it's Hilbert-Schmidt. And the Hilbert-Schmidt norm to the square is the sum of the momentum and of the charge. And in fact, the way to see it is very simple, because if you look at this Hankel operator in terms of Fourier coefficients, you will recover a very familiar formula, which is this one. So this is u hat of j plus k, h hat of k bar. What does that mean? So forget for a while about this bar here. You have a matrix in the basis of Fourier coefficients. A matrix with coefficients which are u hat of j plus k. So you have this matrix here, which is of course an infinite matrix, and which is constant on these anti-diagonals. This is what is called a Hankel matrix. So, and of course you have a kernel here. And to see whether an operator is Hilbert-Schmidt, you just need to prove that the kernel is L2 in both variables. So if you compute the L2 norm of this kernel in both discrete variables, j and k, you get immediately this. Just by, by summing, you get this. And so you recover this formula, which is that m of u plus q of q is the trace of hu squared. Okay? So this is very elementary. So this is the first kind of operator I would like to look at. And the second kind of operator are the so-called Toeplitz operator. So it's even easier, the same as Hankel without a conjugation. Okay? So, but now, of course, the symbol is not a function, a holomorphic function. It may be any kind of L infinity function on the circle. And you just look at the product, BH. But of course, BH pull you H outside of the Hardy space here. So you need to reproject it onto the Hardy space. And this is exactly the Toeplitz operator. Now, this Toeplitz operator is a bounded operator on L2 plus. It's very easy to see. And its joint is exactly the Toeplitz operator associated to the complex conjugation of B. Now, the nice point is that you have a magic formula. The magic formula is that if you look at the right-hand side of my cubic Zager equation, pi of u squared u for any u, and you compute the Hankel operator associated to this right-hand side, you have this decomposition, AU-HU plus HU-AU, where AU is this, Toeplitz associated to mod u squared minus a half of HU squared. So HU squared, once again, HU is antilinear. HU satisfies HU of alpha H equals alpha bar HU of H for any constant alpha. But of course, HU squared is quite C-linear, of course, because you apply both the conjugation. Okay? So HU squared is a nice non-negative trace class operator. And of course, this operator AU is a self-adjoint, is a nice self-adjoint operator. Okay? And now the theorem, which is trivial in view of this identity, is that this equation is completely equivalent to this structure, to this formulation, as an evolution of operators, of families of operators. So assume you have a solution of your equation here, and you look at the Hankel operator associated to this solution, and you take the derivative of this Hankel operator, and you get a commutator of BU, which is just AU multiplied by minus I, so it's a skew adjoint operator, commutator with HU. So why does this anti-commutator, to some extent, became a commutator? Just because you multiplied by I, and because HU is anti-C-linear. So I bar is minus I, and so, of course, you get a commutator. And this structure is well known from people who work with completely integrable systems. And the first, one of the first occurrence of such structure was in the pioneering paper by Peter Lax in 1968 in CPAM, where he proved that Korteweg-de Vries equation has the same kind of property, where HU in that case is just a Schrodinger operator with potential U. Okay? And BU is some kind of third order differential operator. And there was also this nice paper by Zakharov and Shabat in the 70s, where the 1D cubic nonlinear Schrodinger equation was shown to enjoy the same kind of property, where HU then is some kind of Dirac operator. So this cubic Zager equation has that kind of property. what is the consequence? Well, the consequence is clear because you have this two adjoint operator. So if you look at this one parameter family of operators which just solve this linear equations, I assume that you have this function u, small u, which solves this equation, and you look at capital U, which is an operator, which is the identity at time t equals 0, and we solve this operator-valued evolution equation. And then it's easy to see that this operator at every time is unitary, and that the fact that HU satisfies this identity here is equivalent to the fact that HU at times t is exactly obtained from HU at time 0 by conjugating with my unitary operator. So of course you don't know about this unitary operator if you don't know about U, but you know that it exists, and as a consequence it tells you that the spectrum of my Hankel operator is conserved. So it tells you that you have an infinite number of conservation laws. Okay, so all the eigenvalues, and well, because the spectrum, of course, since HU is self-adjoint, I mean, HU square is trace class and self-adjoint, so you have, of course, only a pure point spectrum, and all the eigenvalues are conserved. That's what it tells you. And in fact, it's even better. It's even better, and this is much more specific to this theory. You also have this operator, which is the composition of my Hankel operator with an operator which is extremely important in this theory, which is a shift operator, Tz. So that's just the Toeplitz operator associated to function z. So what happens here? Well, the Toeplitz operator associated to function z, if you look at it in terms of Fourier coefficients, is just a shift. It tells you that it sends the sequence Cn to the sequence 0 Cn. Okay? So this is Tz in terms of Fourier coefficients. Okay? So that's the usual shift on L2. And it turns out that this Hankel operator have essentially the characteristic property that if you compose HU with Tz, is the same as composing Tz star, which is Tz bar also, with HU, and that's also H associated to this Tz bar U. So this first identity characterizes Hankel operators, and it can be shown using the previous Lax pair formula that you also have some kind of Lax pair formula for this new operator, ddt of Ku equals Cu Ku, where Cu is obtained from Bu by some formula. Okay, so it's a rank 1 perturbation of this skew adjoint operator. And as a consequence, the spectrum of Ku is also conserved by the evolution. And if you take the square of this Ku, once again, it's a Hankel operator, but with a different symbol, Tz bar U in place of U, and you get that it's a rank 1 perturbation of HU square. And using the min-max principle for positive compact operators, you get that the spectrum of HU square and the spectrum of Ku square satisfy that kind of property. So the first eigenvalue of HU square is larger than the first eigenvalues of Ku square, larger than the second of HU square, etc. So they are interlaced. Now, the nice thing is that these properties will help you to solve our equation explicitly, so with formulae, as was done, in fact, for KdV, but in some sense in a much easier manner. So let me define good states. So functions which are in H1/2, once again, these are functions in the Sobolev space and the circle, but with a non-negative Fourier modes only, and define the subspace of the subset of this space, which correspond to what I call generic states, which means that the eigenvalues, the non-zero eigenvalues of my two favorite operators, HU square and Ku square, satisfy, in fact, strict inequalities, not only large inequalities as here, but I demand that the inequalities are in fact strict. Okay? So for simple eigenvalues, and all these simple eigenvalues, the mu and the lambdas are always different. It turns out that you can show that this is a density delta. Okay? So this tells you that, of course, there are plenty of such objects, and given such an object, it's rather easy to diagonalize, to some extent, these antilinear operators. Okay, HU and KU. You can find eigenfunctions, EJs and FM, which corresponds to these eigenvalues lambda j and mu m. Okay. Why? Well, that's a little subtle because this is related to the fact that it's antilinear. Okay. You know, maybe I should explain why. If you look at this eigenfunction formula for some eigenvector which is of norm 1, okay? And if you look at HU of EJ, of course HU of EJ also satisfies this formula. And since lambda j square is a simple eigenvalue, you get that HU of EJ is collinear to EJ, and of course the coefficient of collinearity is something with modulus lambda j. So lambda j times some phase factor, okay, omega j, where omega j of modulus 1. Now if you multiply EJ by some, I think it's something like omega j bar a half, then you get that this satisfies lambda j omega j bar a half. Okay? I think it's the right one. No, maybe it's, yes, it is. Yes, so you get exactly, or maybe it's omega j. So if you choose correctly the argument of this complex number of modulus 1, you get a new eigenvector which corresponds to an eigenvalue which is positive. So that's exactly what I did here. You know, it's in some sense slightly different from the standard self-adjoint cylinder operator, and in fact it means that these vectors, these eigenvectors of norm 1, are defined up just to a change of sign, okay? Not to a change of argument, but a change of sign, because it's antilinear. And the same is for KU. And then you define angles, which are some kind of normalization constants, which correspond to the argument of the scalar product of 1 with the first eigenvectors and the scalar product of u with the second eigenvectors to the square. And the fact that you take to the square here tells you that this is perfectly well defined, because if you change EJ into minus EJ, this will not change. Now, the main theorem is that you start from a function. You look at its angle operator and you define, so you assume it's generic, and you define all these eigenvalues, lambda j's, mu m, and you define the angles, phi j's and theta m here. And you define a mapping here. I claim that this mapping is a homeomorphism from this generic set onto a subset of L2 times L2, which is the trivial one, corresponding to the inequalities lambda 1 larger than mu 1, larger than lambda 2, larger than mu 2, etc. So which corresponds to the moduli here. And moreover, the inverse of chi is given by an explicit formula, which is complicated, but completely explicit. You will see it in the next slide. And finally, well, I claim that if you change these variables, the evolution of the cubic Ségué equation is trivial. It's just given by this. So lambda j square are constants, of course, because these are the modulus of zeta and gamma to the square. So this means that the zeta j's and the gamma m's are evolving just by multiplication by e to the minus I lambda j square t and e to the I mu m square t. So of course, the technique is, the method for solving the equation is you start from the data, you convert it into the spectral data, you make this evolve with time, and then you come back with the inverse formula that I'm going to give you now. Well, it's a little complicated, but completely explicit. So essentially, u of z, for a z which is in the unit disk, u of z is given by this, you know. So I don't want to comment too much, but just to show you that this is completely explicit, you know, and only in terms of the lambda j's and the phi j's and the t time. So of course, you could tell me, okay, but given a Hankel operator, I cannot solve the eigenvalue problem. It's a complicated problem, an infinite dimensional problem. Well, it turns out that it's even better. Let me skip this. It's even better because you have a finite dimensional variant of this. In fact, a long time ago, Kronecker proved that you also have special functions which correspond to finite rank Hankel operators, and these finite rank Hankel operators correspond to rational functions of the variable z, okay? And then you have a manifold, given the rank of the operator, you have a manifold which is a complex 2n dimensional complex submanifold, and on this you have a standard Hamiltonian system in finite dimension. And you can write the equation which is here by decomposing u into a sum of elementary rational functions, say alpha divided by y minus z p, okay? So in terms of poles and residues, and you have a system of 2n ordinary differential equations, which are completely explicit. I didn't write it here because it's a little long, but it's explicit on the poles and on the residues of this rational function. Or S is this equation, the Zeger equation. Okay. So if you look at the open subset which corresponds, so you have the same kind of generic sets, but now it's a dense open subset, and except that of course you only have n non-zero eigenfunctions, eigenvalues, since it's a finite rank operator. And once again, you have a mapping which is now a C-infinity diffeomorphism, not only a homeomorphism. And in fact, this is symplectic in the sense that you conserve the symplectic structure. You have canonical coordinates. And so you have, in the Liouville theory, these coordinates are called Birkhoff or action angle coordinates. So it tells you that you can completely solve these 2n equations, and even for n equals 2, this is not trivial. You have a system of 4 ODEs that you can solve really explicitly, because now you have an operator which is of rank 2, so it's a 2 by 2 matrix, and this you can find, of course, the eigenvalues. Now, I think I'm essentially done, but I just wanted to mention, among many others, an application which is that we can in fact characterize, there are special solutions which are not generic of this equation, which are solitons. So solitons are functions such that if you multiply by some phase function, some phase factor here, and you make some rotation on the disk, on the circle, then you have a solution of the cubic Zeger equation. So equivalently, they are solution to this very strange equation, a nonlinear equation. So let me remind you that d is just 1 over I d theta, okay? And it turns out that we can characterize all the solitons of this cubic Zeger equation. Well, they have some properties here. I don't want to comment too much. I don't have time for that. But there is one which is very particular, which is just this. Okay, so just a rational function with one pole. And it's an optimizer of some kind of Gagliardo-Nirenberg inequality, a little like in the nonlinear Schrodinger theory. And this Gagliardo-Nirenberg inequality helps you to prove that this soliton is orbitally stable. Okay. And it turns out, and this will be my last slide, it turns out that this is the only stable soliton because you can use the explicit solution of the equation by means of my action angle coordinates. It's a little complicated, but very explicit to prove that all the other solitons are orbitally unstable. So of course this inverse spectral theory for Hankel operator is very, very important for studying the geometry of this equation. So just in one word, the prospect, there are many. Okay, so the HS norms, for instance, there is a very important difference with the other completely integrable systems like KdV or nonlinear Schrodinger, which is that if you look at all the conservation laws, they do not control the HS norms if S is large. Of course, they control H1/2. This is one of them. But they don't control the HS norms for S large, which means that you might very well have evolutions which are not bounded in HS. This is, in fact, an open problem. You can also try to replace the circle by the line. So you work on the line, you have the same kind of properties, which it's still, of course, an integrable system, but it's even more interesting to some extent because you have new features. In particular, you have asymptotic stability of solitons. You have that you have much less solitons. Essentially, you have just one, but all the solutions as t large goes to infinity, not all, but a large class of solutions expand as a sum of solitons for large time. Okay, plus something which goes to 0. And this is a work of my PhD student, Oana Pokovniku. It's a work in progress. It's also interesting try to find weak solutions in even weaker spaces, not H1/2. H1/2 is not really, it's natural from the viewpoint of course of the momentum, but typically the most natural space would be the energy space, L4. How to solve this in the energy space? Then, of course, the Hankel operator are still defined, but they are unbounded operators. So you have to do some spectral theory for this unbounded operator, and to some as far as I know, it's not known. And they are also, of course, you have to come back now to our original equation. And of course, you would like to know, is there a similar structure? Probably not exactly, but approximately maybe. If you deal with, for instance, small data, we may expect, because if you make some computation, you are not so far from this. And a little like, if you pass from constant coefficient linear equation to variable coefficients, you know that Fourier transform for variable coefficient does not work so good, but you also have some asymptotic theory, which is the theory of pseudo-differential operator. So to some extent, you may expect that you can do that thing, and a toy model for that would be to do some Kolmogorov-Arnold-Moser theory on an intermediate toy model, which is this equation. It's just a wave equation on the circle or on the line, where the Laplacian is replaced by minus mod d. So, of course, the most natural thing to do is to decouple positive modes and negative modes. And if you decouple that, you get, once again, a system of two transport equations with right-hand sides which are of that kind, pi plus, and pi minus of u squared u. And it turns out that you can prove that you have some decoupling for small data. And Birkhoff normal form theory gives you some hope that you could perform some KEM theory for that. So which could be already a good step in the direction of solving such a degenerate nonlinear Schrodinger equation. Thank you very much for your attention.
We have some time for questions. If anybody has, please.
Just can you show me the lax sphere?
Of course. Okay, so you need Hankel operators, okay, and tuplets, okay, and the main formula is this one. So h pi of u squared u. So of course, if you have this equation, I should write it maybe in a slightly different way. du dt equals minus I pi of u squared u. And now you start from such a solution and you look at ddt of hu. But this is linear in u, so this is h du dt. And now you replace du dt by this, and you apply this formula, and you did exactly this. So this is very, very elementary. But the nice thing is that, of course, it gives you all these conservation laws, spectral conservations. So that's the same spirit as KDV or NLS, except that the Lax pair, I mean, the first part of the Lax pair is completely different. It is an operator of a completely different structure, this Hankel operator. And it turns out that the inverse spectral theory for Hankel operators that we had to do for solving the equation is a new thing. It's a new thing. And we used, in fact, techniques from symplectic theory for proving that all these homomorphisms are, in fact, one-to-one and onto. Okay.
Any other questions? Okay. So if there are no other questions, we will have a 10-minute break. We will start at 3:05. And thanks again.